and then his work also spans food rheology, the topics that will be discussed today, and then others research topics. Professor Imam Books has an extensive publication record and has received multiple awards, both internationally and nationally. And then he actively supervises postgraduate students and postdoctoral researchers. I think we can give a round of an applause to Professor Nausad Imam Books. We welcome him to this guest lecture. So today's lecture will be presented by Professor Imam Books, titled Introduction to Food Rheology and its Application in the Food Industry. So let us make the most of this valuable opportunity by engaging actively, listening attentively, and preparing questions for the discussion session at the end. So without further ado, please join me in welcoming Professor Imam Books. Professor Imam Books, the microphone is yours.
Yes. Hello, good morning, everyone. And thank you, Dr. Tina, for such a nice introduction. I'm really pleased to be here to share some of my insights in food rheology. But I just want to make a disclaimer, please, that I'm not a rheologist. So I don't do like what we say fundamental types of rheology research. But what I do is use rheology as a tool in food. Okay, so this is what. And today, I think for you to use that, you will need to learn a few of some of the what's called fundamentals of rheology. Okay, can you hear me, Dr. Tina? Yeah, properly. Yeah. So
Yes,
what I'm
we
going
can
to
hear
do
you.
now, after you saw me, I'm going to switch off my what's called my camera so that it's easier also. And I'm going to start sharing my presentation. Okay, let's see now. Window, let's see if it's going to share this window. Okay. Can you see my PowerPoint, which is not yet? You can see it, Dr. Tina? Yeah, you can see it. Okay, so I'm
Yeah,
going
we can see
to
it.
what's called put it on PowerPoint mode and then we will start. Okay. All right. Okay, if there's any problem, please let me know. I think I'm very far from all of you. Okay, sometimes there might be some issues in the bandwidth or the internet. So please, let's call, give me, just put a thumbs up or a question mark, or you can stop me, Dr. Tina, if there is a problem with the internet. Okay.
Yes,
So,
Professor.
like Dr. Tina said, yes, I am from the University of Pretoria. And the University of Pretoria is situated in South Africa, in Pretoria. Pretoria is the capital city of South Africa. And what you see here, there is a pointer. Here, it's what is the administration building of the university. It's called a skip or a ship. Okay. All right, and then here, what you see here, this is also we are based in a heritage building. Okay, and this is where I building where I stay, where my office is at the university. Okay. All right. Okay, if you look about food rheology, I think the definition that people talk about rheology is really the study of the deformation and flow properties of matter. Okay, and it's a well-known field, whether it's in mechanical engineering or chemical engineering. Okay, in the engineering part or material science, it's very well-known science. And then it has been applied in food maybe about 20, 30 years ago or more. It has started to apply. And it's still been a very good way to characterize food or to predict food also. Okay, and if you think about rheology, it's involved in a lot of processing. Okay, deformation and flow. I think a simple example that we can take, I put an example here, I didn't mention it here. Maybe you guys can think about, and Dr. Tina, can they interact in the lecture? Can they write, for example, in
Uh,
the
yes, in the chat.
chat they can write?
Yeah.
Okay. So if you think about rheology, maybe what's called scholars who are attending today, if you can just maybe mention in the chat, do you think there are places that where you can use rheology? I can give you an example, one very simple example on a daily basis that perhaps something that you eat. I think whether it's bread or maybe not Indonesia, mostly rice, but in South Africa here they will do eat a lot of bread. Or in Europe they eat a lot of bread, and you need to make a dough from wheat flour, and from the wheat flour you made bread. So the dough that you're making, there is a lot of rheological process that is formed there. So during the dough making itself, you add flour with water, you change the properties of the flour and make it into a dough. A dough, you need to deform it, and then afterwards, when you bake it, you need to make sure it can hold a bubble. Okay, that's an example. So there should be certain rheological properties. And gluten, which is in the bread, is very important there to provide this property. Okay. And Dr. Tina, I understand that these are all students doing food science. Am I right?
Food technology. Yes.
Food technology. Okay, and they are mostly in their last year or all the years?
All the years.
Oh, all the years. Okay. All right. So I think, yeah, okay, never mind. All right. And the other thing is when we eat in our mouth, there are a lot of rheological process that is happening. If you think about, again, a piece of bread, like you see it on the table, and then you put it in your mouth, okay, it's a completely different structure now once you are start masticating. Your saliva is mixed with the bread and it become a bolus, and then you swallow it. Okay. So for example, the mastication that happen in a child, which is about 6 to about 24 months, compared to, for example, a growing child from 24 to adulthood. Okay, an adult. Okay, and then the mastication that happen after people who are 70, okay, who is especially suffering with what's called chewing problem, as well as swallowing problem. Okay, so the chewing and swallowing problem is happening in all people and it's called dysphagia. Okay, so these, for example, need to be addressed. So we need to have food that have different deformation and flow properties when we are eating it. Whether it's for a small child, for example, less than 24 months, or especially the one from 6 to 12 months. Okay, these child need to have more like a liquid type food. Okay, because they can't masticate and they can't swallow properly. The same thing for an old people that suffers from dysphagia. There should be some ways where food should be a little bit thickened, okay, so that they can swallow it without the food going in the windpipe, for example. So rheology is like I gave you an example on our daily life, making bread, or during mastication. When you masticate, you change the deformation and flow properties of your matter, or you are deforming your food material in your mouth. Okay. And when you talk about rheology, people generally talk about solid that have elastic properties. And when you talk about liquid, we look at mostly viscous properties. Okay. Viscosity is more resistance to flow, and elasticity is more like when you deform something, it can go back to its original shape. Okay. And this is what we talk about solid and liquid, but most food are especially mostly semi-solid. If it's solid, we might break our teeth. Okay. And if it's too liquid, we don't really drink too much. I mean, we need to have solid, semi-solid food mostly. Okay. That's the most important thing to remember. The next thing is most food is made up of food biopolymers. If you think about protein, it's a biopolymer of amino acid. If you think about starch, it's a biopolymer of glucose. Okay. And if you think about non-starch polysaccharide, again, it can be biopolymer of several type of sugars there, like the xylose, for example. So all these biopolymers now, they interact with each other and provide some rheological properties of food. Okay. And it's mostly semi-solid. And when we talk about semi-solid, generally it has both the elasticity and the viscosity. So it has both elastic properties and viscous properties. That's why we always talk about food being viscoelastic, have viscoelastic properties, because it has both viscous properties and elastic properties. Okay. Now to sum up again, remember rheology is the study of the deformation flow of matter, deformation and flow of food material. Okay, we use rheology in our daily life, whether during food preparation or mastication. And most food are viscoelastic material. Okay, I tried to put you some of the food here and now some of the things that we do on a daily basis. Like, for example, we can have a glass of beverage here, very liquid. Okay, if we have cream, for example, here, all right, but when you beat cream, it can form, you can produce a foam, like, and like, for example, a mousse, which is a type of food. So from cream to a mousse, there are different properties that we are looking for. Okay. And cream is used a lot in your daily manufacturing of food or daily cooking also. Okay, for example, you got a chewing gum. Chewing gum is more like a semi-solid, I will say. See, if you blow a chewing gum, I think here there is a biaxial deformation. You are blowing it in all different directions. Okay, you have jellies that we generally eat all the time, and you know, when you make jelly, you start with a powder, you add water, and then when you set it, it becomes hard. So these are some of the rheological properties that are changed. And when you make jelly, for example, you add sugar also there. Nowadays you need to have diabetic jelly, and sugar is important for the it does impact the gelling properties. So how do you make, for example, a diabetic jelly that doesn't have sugar without compromising the gelling properties? Okay, you eat an ice cream. Okay, it's very different. It's very complex system here. You got dairy, you got fat, you got milk. Sorry, you got protein, you got fat, and you got ice crystal, very small ice crystal. Okay, and then it has to stay solid. Okay, and it melts, it become more or less like a fluid. So there's certain rheological properties that change here. And another example is in a tube where you are pushing food out. Okay, if you take the tube upside down, it doesn't come out. You need to squeeze it for it to come. And if you squeeze it, you want it to stay on your finger. For example, this is a toothpaste. Okay, you don't want it to flow out. It's flowing out of the tube, but still when you put it on your finger, it stays there. Okay, so you need to have certain what's called rheological properties for that. Okay. I don't know if anybody has any question yet.
Anyone, if you have any question, you can raise your hand. Maybe there's no question up to now
Okay,
from.
so we can carry
Actually,
on. Okay.
it
So
seems I have one.
Oh yeah.
yes.
Fauzan, please.
Does rheology also involve some sort of in biologic as well, like, hydrolysis? Wait, that was chemistry. Yeah, actually that.
Yes, okay. Yes, so if you look at hydrolysis in biochemistry, like for example, one can use it to predict what is happening. Because, for example, if you have starch is highly viscous. Okay, when you hydrolyze it with enzyme, it becomes the viscosity decrease. So, for example, one can use it to predict hydrolysis, for example. I think that one way what can look like. Currently, we are involved in a very small project where broiler chicken or chicken is fed different type of food, and to look at the digestibility or feed conversion efficiency, they took a little bit of the digester in the small intestine at the ileum level of the small intestine, and then you can measure the viscosity, and the viscosity can already tell you what is happening to the digester, whether it's hydrolyzed or not hydrolyzed properly. Okay, does that
Okay,
answer your question? Yeah,
that's answer my question enough. Thank you, Mr.
thank
Naufal.
you. Okay, yeah. Okay, so where is the big relationship in food science and rheology is really to look at food texture and food sensory, food sensory properties. So everybody that eat food, there are two components there. We eat food for nutrition, okay? But for me, everybody in the room here, I mean, we eat food really also when it's nice. Okay, when it tastes nice, it has certain texture, it tends to have certain flavor. Okay, so rheology can be used there to predict the sensory evaluation. If you think about sensory evaluation, it's quite what is it called? It's quite a very tedious process and also an expensive process. Okay, and certain food, which is especially at the when you are developing it in the lab, and if you don't have proper what's called process that you use so that it can be safe for the consumers, you can't do sensory evaluation. So this is where rheology come into place. So if you look at texture, even flavor, when you eat food, it's mixed with saliva. There is thermal sensation and auditory cues here. And also there's physics here that affect the texture. And rheology actually affect texture of food. If you think about a gel, okay, if you don't add enough what's called material solid there, it might not form a nice gel and it won't have this nice texture. So this rheology here is, if you think about a gel, is due to deformation and flow properties, and this is affected by the molecule you're adding and the microstructure. That's very important. When you look at rheology, there is this triangle here: the molecular structure, the microstructure, and this affect the rheology directly. On the other hand, also molecules that is made up in your system, for example, in your dough, what molecule you have? You have starch there, you have proteins there, which is mostly the gluten that has been developed, okay, from wheat protein. And this create the microstructure of your dough, their gluten network that is formed that can hold bubble. And if it can hold bubble, it can rise, okay, and form like more or less like a foamy type structure during proofing when you're making bread. And then when you bake it, it becomes more like a sponge, like a solid. And then when you eat it, your bread need to be held a little bit fluffy in term because there are lots of air. It's very dense, it's very hard. There's lots of air bubbles, it becomes very soft. Okay, based on the rheological parameters, okay, in terms of dough rheology, like you can measure the torque when you're making the dough, or you can measure how much volume there is, or there are other rheological measurement that you can make. You can predict what sort of bread texture you will get. This is an example, a simple example. Okay, so let's see here now. So I got two things here. I got a very fluid here, like a tomato ketchup here. Okay, and we got some very hard cheese here. So when you look at hard cheese, what we do generally, we do mostly, it's mostly solid like nature. I'm not saying solid because most material are mostly viscoelastic, has certain viscous and elastic properties. Okay, but we talk about solid like nature. We look at that, for example, cheese, we look more like the deformation and melting properties. Okay, You don't want a cheese so hard that it's going to, when you eat it, you can break your teeth, but it has to have certain hardness depending on the type of cheese. And when you add, for example, your cheese, whether it's Gouda or other type of cheese, other type of cheese on your burger or mozzarella, wherever, or on the pizza, you want it to melt at a certain temperature. And rheology can show that what is the melting temperature you got. Another example is that it depends what you want. Sometimes people want the cheese on your burger to melt, and sometimes you want it not to melt too much. So just to soften, but you want your burger to stay hot. So there should be a temperature that you store your burger so that your cheese doesn't melt too much, become very liquid-like. So you can measure the melting point using rheology for your cheese, for example. And liquid line nature, I'll tell you mostly flow properties, example, juice and tomato. Okay. When you talk about rheology, there's two types when you look at that, when you do the measurement or when you understand the science. It's called large deformation and small deformation. Okay. We will explain to you what is the two different in terms of it. But before, my idea here in this lecture is to let you know, when you look at a manuscript or when you look at book that talk about rheological properties of food, there is certain terminology that they use. Okay, if you can understand these terminology and where it's come from, it will be, then you can understand the book, and you can understand the scientific paper you are reading. Okay, sometimes they talk about deformation, which is tension, compression, and shear. Some people talk about stress, strain, Young modulus, and shear modulus. What are these? People talk about Newtonian and non-Newtonian, especially for fluid. Okay, viscosity, shear viscosity measurement, yield stress. And people talk about elasticity, viscosity, and viscoelastic properties. And people talk about storage modulus and loss modulus, whenever you will do. Or certain people will talk about tan delta. Okay, when you read these papers or book chapters for you to understand rheology. Okay, and these terminology is very well known in material science. So we'll come to, let's look at the large deformation first. Okay, so I think this is quite clear here. When you have a material, you pull apart is extension. Okay, here you pull it apart, you apply the force in opposite direction here. Okay, it's extension, and it's another word that people use to do that, to look at tensile properties, and this is mostly used for example, plastic packaging material. Okay, compression, you have your food and then your force is perpendicular to the plane here. If you have your force here is perpendicular. Okay, so then you have compression. This is mostly due for mostly cheese, for example. You can look at fracture properties of food, or a gel, for example, you can use that. Okay, and shear. Okay, shear here, your force is also in opposite direction here and here, but the deformation here is basically has a angle of deformation here. It has an angle here. Okay, so extension, I think, and compression and shear has an angle of deformation. Extension, you're pulling things apart. Compression, you're compressing something. And shear, you have an angle of deformation. If you think about here, there is an angle of deformation here. Okay, so the issue is that, problem is that always people do this some type of errors when they look at when they do deformation. You can use, for example, a texture analyzer to do the first two. Okay, third one, you really need a rheometer to do look, especially angle of deformation. Okay, so yeah, so a texture analyzer sometimes the main problem that people always do with textual analyzer is that it's very difficult to interpret the results if we don't know what probe you've been using. Okay, and to compare results, very important in texture analyzer, if you're doing extension and compression, you need to have the same size, more or less. Okay, because if you extend something or compress something, the bigger it is, the more force you will need. Okay, but in rheology, there is a way to normalize this. So what you do, then you change the extension and compression. The force here, you will get it in terms of Newton. You change it in terms of, you make it in terms of stress. Okay, so what is stress here? The stress here is sigma, which is force divided by the cross-sectional area. And force is Newton, A is in millimeter square. So sigma is Newton per millimeter square or megapascal here. Okay, strain here is you change, you measure another thing, which is change in length divided by the original length. So whenever you do texture analysis, think about that. If you can do something where you can have the stress and strain, is better than just having the force as what's called as Newton. Okay, so the idea is the bigger the cross-sectional area, you will need a bigger force. Okay, but for one material, for example, if you think about a gel, like a gelatin gel, for example, if you have a small gelatin gel, which is, for example, like a disc, okay, which has a diameter of 1 centimeter, compared to a diameter of 2 centimeter, the 2 centimeter, you will need more force in terms of Newton. But if you normalize it in terms of stress, you divide it by the cross-sectional area, you will have similar stress. Okay, so the bigger the cross-sectional area, the more force you will require for one specific material. But for stress, it should be the same because you normalize it. Okay. Can I have, for example, maybe a thumbs up if you understand this concept? Anyone?
Anyone, if
Or
you
you have any?
understand this concept, please thumbs up. Yeah.
Okay.
Yeah. Yeah. I
It's
think.
thumbs up. So can I carry on now? Okay.
Yeah.
All right. So another way to represent this. So if you have a like a more or less like a piece of what's called a square, like a cuboid type of gel or a plastic film, sorry, you are doing extension here or tension, extension and tension, you measuring the tensile properties. The dark blue here is the original length and you pull it apart. So the stress will be the force that you need to pull it apart divided by the cross-sectional area here. And the strain will be the change in length divided by the original length. Okay, did I mention here? Okay. All right. So if I may ask you, stress, I told you what is the unit here, Newton per millimeter square or megapascal. But if you have strain, what will be the unit of strain, if I ask you? Anyone? Delta L divided by L. So what will be the unit there?
What is the unit,
Anyone?
guys? Anyone?
Unit for strain. Okay, maybe you know it. So length divided by length. Okay, delta L is what will it be? A length, what will be the unit of length? Anyone, perhaps? So the difference, if for example, you start, maybe this is 5 centimeter, it becomes, for example, you extend it and it becomes 6 centimeter here. So the strain here will be 1. Okay, 6 minus 5, which is 1. And what will be the unit here? Will be centimeter. And the initial length will be 5 centimeters. So it's 1 centimeter divided by 5 centimeter, which is like 0.2 or 20%. Okay, so it's centimeter divided by centimeter is cross out. So it means that the unit is, there is no unit here. It's unitless. Strain here is unitless. Okay, whereas when you look at shear, the force here, you will get again sigma here. Okay, what's called tau here generally, or sigma if you want to say, force divided by area. And strain here, it's an angle. Okay, if you remember your trigonometry, okay, so this is the angle of deformation. This is opposite and adjacent. You should be able using tan to get it here. It's just the opposite divided by adjacent. So you can get the angle using trigonometry here. Okay, I think everybody is familiar to trigonometry a little bit that we learn maybe in high school. Okay, so the idea is when you look at now, if you look at a deformation curve, you will get these things, stress and strain here. Okay, let's see now. Stress is megapascal, strain is unitless, or you can put it as a percentage if you want to. Okay, and then you got, generally you got these 3 types of curve here. You got, this is the ideal curve here that you can get. Okay, when something is fragile, it just go and then it snap. Okay, if you have a plastic films for packaging material, you don't want it to snap that quickly. Okay, all right. Oh, something which is ductile means forever, for a very small what's called force you apply, okay, it tend to move, it move, it extend without breaking. So it's very ductile. You also don't want that. Otherwise, if you have a plastic bag which is ductile, you will go shopping and you will put your food in it. Your food will exert certain force because of its weight. You carried it. By the time you reach home, your plastic will extend up to the floor. You don't want that. Okay, or you don't want that. It's so fragile that the moment you put your food inside, it will exert certain force, and then it open, or what's called, it tears, and then all your food go out. So you need to have your plastic bag that doesn't, it's within, if you look at the blue graph here, it's below the yield point here. There is hardly any deformation. Okay, all right, so the other thing that I want to say here, if you look at the blue graph here, if you look at the blue graph, it's like more or less like a straight line here. Okay, and then it and there might be slightly more and it's snap here. So with the yield point here, we talk about yield point. What is yield point? Another rheological term here, you need to understand it, is if you stop your deformation at yield point, it's reversible. It can go back to its original shape. Beyond the yield point, it's irreversible, means you have a permanent deformation. So what is also, when there is permanent deformation, also we call it sometimes large deformation. So below the yield point, it's reversible. Above the yield point, it's irreversible deformation. Okay, that's what we wanted to show you here. Okay, do I have it here? So let's see what's application in food now. Okay, so stress. Okay, so see for example here, you have bread. If you have a bread, you cut it into slices or wheat buns. Okay, and then you do a compression test. Okay, the compression test, what tend to happen, it give you the stress, and this is log time, I think in terms of minute. Okay, all right. Oh, I think it's 200 this is 1,000 minutes. No, I think it's 1,000 hours here. Okay, it's hours here. Okay, and it measures the stress. It's from a paper, very long time. So you will see more or less like 10 hours, it's still fine. Okay, all right, it's still okay. More or less in between, maybe during the day. And as you go along more than 100 hours here, it start increasing sharply or exponentially. Okay, so you can see that bread harden, and the hardening of the bread is quite a what's called on the log scale. It's quite it increased very tremendously after 100 hours. Okay, so what one can see here now is that you can do that. Okay, and then you can do a sensory evaluation also, so that you can feel when does people feel that which stress of the bread that people can reject the bread. Okay, so when you look at the stress, see for example, if the stress is 50 megapascal, then you can tell them this is the shelf life is over. Okay, if 50 is the level where the consumer feel that it's too hard. Okay, so you understand that bread, if you leave it, it get hard and then you don't like to eat it. Okay, so this is 50, and then you can see here when, for example, the shelf life. If it's 100, you can also find out when is the shelf life is over. Okay, but people maybe prefer mostly if, for example, 50, then you can do that. Then what you can do, you can change the formulation. Okay, you can add, for example, monoglyceride, or you can add enzymes. This soften the bread. Okay, and if softened, that can increase the shelf life. So that's an example where stress and strain can be used. Yeah. Okay, if you think about two types of material now, we talk about a biscuit and we talk about jelly tot. Do you guys know about jelly tot or jelly baby, jelly gums? You know about it? Anyone? Do you have the jelly gums at your place in Indonesia? You got it, am I
Yes,
right?
yes,
Yes,
sir.
or jelly tots, yeah. Okay, so if you think about these two food, okay, biscuit, you want it to have brittle fracture, am I right? Crunchy, and then it's good quality. If you have a biscuit, when you're having to eat it, it doesn't snap. Okay, for example, it don't break very quickly. Okay, you don't have these crunchiness, or it doesn't make the noise when you break it. Means it can add water absorption here in its bad quality, especially in Indonesia where the relative humidity is high. When you buy a biscuit, you have to put it in an airtight container, am I right?
Yes, that's
Yes,
correct.
so that it doesn't you don't lose the crunchiness. Okay, on the other hand, if you have jelly babies, okay, or here in South Africa and other places, you have a lot of jelly tots. Okay, here you want it to have it's chewy, and even if you take it, you pull it apart, it pull apart a little bit. Okay, it's not hard. Okay, and if it you leave it outside, it lose some of the moisture and rearrange itself, then there is bad quality, it becomes very hard. You don't want that. Okay, so just to show you like a hard texture compared to, you can do a large deformation here to look at good quality and bad quality biscuit or jelly tot. You can also use it to look at shelf life in terms of texture and relate it to sensory evaluation. Okay, so this is an application. Okay, all right. Okay, so do you, let me finish this one. Just to look at the typical fracture parameters here. Large deformation. Okay, you have the stress here, which is the y-axis. You got the strain here, which is the x-axis. You always got the yield stress. The yield stress where you have beyond that or after that there's permanent deformation. And before that you got what's called reversible deformation. Okay, we'll just stop here and also look at the biscuit here. I want to ask if anybody has any question. Anyone? Okay, so if
Yeah.
thumbs up if you understand some of the concept properly now. A little bit. Obviously, you won't understand everything. You need to go back and read about it. Yeah. Okay. All right. So when you talk about typical fracture parameters now, if you go beyond the yield stress is permanent, and if you go lower than your yield stress, it becomes reversible. And if you look at here, that part here at the beginning here, it's mostly a straight line, and we have a slope here. Okay, and if you work within where the slope is the same, this is where you can do small deformation, okay, where it's a reversible deformation. So remember earlier we tried to talk about large deformation and talk about small deformation, and here when you look at the extension, what's called it's represented as E, okay, which is this modulus, okay, and here when you look at moduli here, all right, here when you look at stress and strain here, which is megapascal, here strain is your percentage or unit less, okay, it's a Young modulus here is ratio of stress strain when is elastic solid material is compressed or extended. So you talk about Young modulus of elasticity, they can call it. Modulus measures stiffness of an elastic material, the elastic portion. Okay, use modulus of deformity as food. They are viscoelastic, but also when you talk about the most food of viscoelastic and this moduli, we can change, we can, what's called, we can basically turn it or differentiate because of the viscous component and the elastic component. And this is what when we do small deformation we can do. Okay, here it's mostly Young modulus when you do a tensile or compression. And when you do a shear deformation, it becomes generally shear moduli or the ratio of the shearing stress to the shearing strain. Okay, Young modulus is mostly for compression and extension. Shear modulus is the ratio of the shearing stress to the shearing strain. So when your stress and strain is a straight line, you can calculate these and give you the stiffness of your material. Okay. All right. So we talk about elastic and viscous. In nature, there is no such thing as a pure elastic material or a pure viscous material. So most are viscoelastic. But from a theoretical point of view, people has work on ideal solid, okay, and ideal fluid. Okay, they talk about ideal solid followed Hooke's law. I mean, tensile strain is applied to an ideal solid. A tensile develop a material that is directly proportional to the strain, which is a straight line. So they put this picture here is about skin. Our skin can be seen out maybe quite a very elastic material. Okay, and with time the elasticity change also. So one way to work on to keep the elastic properties of our skin, lots of people use anti-aging cream, for example, or can use cross-linking to cross-link the protein in the skin. So one way to measure it, for example, people in the cosmetic industry can use what's called artificial or skin of animals to look at what happened there. Okay. Okay, now we come to the term viscoelastic. It's a material that exhibit both viscous and elastic properties. So I try to explain this very simply here. I don't think it's as simple, but just for today, we can look at it here. If you have an elastic material, if you have a, for example, a cube, you apply the stress here, or maybe a cylinder, you apply the stress here, you can have a shear stress here. You remove it, it goes back because it have lots of storage energy here. Viscous material, it mostly lose energy and there is permanent deformation and it flows. Viscoelastic, it has both the loss and the viscous, sorry, the storage and the viscous proportion. Okay. So elastic material, we look at it more like, for example, the storage modulus, or and viscosity, we look at the loss modulus here, what it is. So measure of viscoelastic properties of material. What we tend to do, we tend to always work it into the linear viscoelastic region. So it's a small deformation. There is no permanent deformation or fracture. Also, we have some oscillatory strain. Okay, we will talk about it. Here, stress is proportional to strain in phase. Ideal liquid is Newton law, and we talk about ideal solid follows the Hooke's law. Okay, and I'm sure this is quite very not familiar to you yet. Okay, but we will go the next few slides, we will talk about it into more detail, and you will see there are some repetition, and I'd like to repeat it so that people, I mean, as scholars can learn a little bit more when there's some repetition. Okay, Tina, I don't know if your student want to take maybe 5 minute break just
Okay.
to stretch themselves.
Yes, I think we
Yeah,
can take 5 minute break.
yeah, okay. A 5 minute break and then we carry on.
Yes.
Okay. Hello, Dr. Tina. Should we carry on? Yeah.
Yes, yes.
Yes. So do you think we should carry on or have a discussion and maybe do a second lecture on the measurement of viscoelasticity? What do you think, Dr. Tina? Is it not going to be too much for the student? It's up to you. Yeah.
I
I
think
can
most
make
of the
myself
students,
available in the next, yeah.
yeah, most of the students already studied about food rheology. So I think
Oh, okay.
the material is uh okay for them. Yeah, most of them.
Okay, all right. All right. So let me carry on then. Okay. Continue to share. Okay, so when you talk about what's called small deformation, always in linear viscoelastic region, small deformation, there is no fracture here. And we saw when you look at small oscillatory strain to sample, there are three things we need to remember. It follows, which is Hooke's law, which is stress is proportional to strain. They call it in phase ideal, and also follows the law of Newton law, which is the stress is proportional to strain rate, which is out of phase. Okay, for viscoelastic material, it has both properties. And it's also the same thing, like if you have a ball, you let it drop by itself because of the material it's made, it has certain both elastic and viscous properties. So it has some storage energy as well as it will lose some energy. So it won't go to the same uh, level, okay, as we do here. It will not go to the same high, go back to the it's after it bounce. Okay, so when we measure viscoelastic material, so what happened here in a real meter now, for example, here you can have a motor here, okay, that will have certain strain, okay, that will be applied, okay, and the stress is measured, okay, and the strain and stress is within the linear range, so you will get the moduli, okay, and that's the first thing. And because it is based on the law here, what tend to happen is that there will be some in phase and there will be some out of phase material. Okay, so this is what we have here. All right, if you have a Hawkonian solid, it's what is called in phase. And if you have a Newtonian liquid here, it's out of phase by 90 degrees, so there's a delay. Okay, and then for viscoelastic material, it's between 0 and 90 degrees, the out of phase, the phase change. Okay, so the Suna input and strain responses for elastic solid, viscous liquid, and viscoelastic material is between 0 and 90 degrees. Okay. So see, again, I want to show here, see, for example, here is more or less the angular frequency that you're having a material, okay, and then this is your setting of the strain, and you're measuring the stress here, okay, and then there is something which is, there's a phase shift, okay, here, which is delta, that the rheometer can measure. So this is what the rheometer will measure. You put in a strain, it measures the stress, and then it also measures the phase angle here. Okay, the phase shift, like what we say here. Presetting strain with an amplitude here, an angular frequency, okay, and how this is how you calculate angular frequency, and I'm not going to go into detail. So as a result, you got the shear stress and you got the phase shift. It's a time delay for the test response compared to the exciting sine curve. There's a time delay here. Okay, so you know that that is the delta, which is the time delay. You can make the phase shift here. And then with the stress and strain, you can get the complex shear modulus. Okay, and the complex shear modulus has two components here. It contains the storage modulus and the loss modulus. Okay, so this is, if this is the storage modulus here, this will be the loss modulus, and then you have the complex modulus and you got the phase angle here. Okay, so what the machine do, it you can measure it can give you as an output, which is the complex modulus. The complex modulus is based on the shear stress and the shear stress and the shear strain, or the shear stress divided by the shear strain within the linear region. And then the machine can also give you the phase angle. So if you have the complex shear modulus and the phase angle, you should be able to calculate the G prime and the G double prime, okay, based on trigonometry principle. Okay, so G prime is the storage, okay, and modulus, and G double prime is the loss modulus. And tan delta here, okay, is the G double prime divided by the G prime. So the loss modulus divided by the storage modulus, which is the damping or loss factor. Okay, is the quotient of the viscous and elastic properties. All right. So this is just a repetition. Okay, relationship between a strain is modulus. For elastic solid, it is mostly in phase with the shear strain is defined storage and elastic modulus. For Newtonian fluid, stress component is 90 degrees out of phase with shear strain. This is defined as the loss of viscous modulus. A viscoelastic material will have both viscous and elastic moduli. Loss divided by storage modulus is G prime divided by G prime, which is the loss factor, which is the tan delta. Okay, so it means that for a completely what's called Newtonian, there will only be the G double prime. So that's why the loss tangent will be 0, and then it's 90 degrees. Okay. Again, I want to show here just to compare again. So if you have your shear complex, shear modulus here, and then you have the phase, you should be able to calculate the G double prime and the G prime. Okay. So what we've dealt with a large deformation, which is permanent. We've dealt with it. Small deformation is within the linear viscoelastic range. Okay. So this is what we want to do. So whatever rheological parameters you are measuring, first you need to calculate what is the linear viscoelastic range. So again, if you remember here, the stress strain curve, we talk about the linear viscoelastic range where it's linear here, where the strain is linear with the what's called stress, and then you get a constant modulus here in terms of the shear I mean, here is the Young modulus of elasticity here, for example. So how do we do that? How do we calculate the linear viscoelastic range? So what we do a strain sweep, or what's called strain amplitude sweep. So what we do, we increase the strain. Okay, and then you measure the G prime and the G double prime. So your G prime and G double prime should be straight line, or the complex shear modulus should be a straight line here. It should be independent of the strain. But when it's coming dependent or its change goes, then it becomes a non-linear viscoelastic range. Remember that again? The slope here till here is the same. And the slope here is what they will give you the modulus. So it's the same here. So first we need to calculate the linear viscoelastic range. So you input strain and then you increase it. You have a sinusoidal strain and then you measure the stress. It should be proportional until you get it not proportional, and then this will be the non-linear, this will be the linear. So whatever you do in rheology, if you want to measure the viscoelastic, you look at the linear viscoelastic region. Now, for example, I just give an example here. This is the gel development of a gel material. For example, you have a solution of gelatin, and then afterwards you let it cool down, it becomes a solid. So you can put it in a rheometer, and then you can measure the storage and loss modulus. So you will see here the first graph here, which is lower at the beginning. This is the G prime, and then after which it take over, become higher. And here there is at the beginning, the G double prime can be higher, and then it become lower than, and it plateaued and become lower than the G double prime. What is trying to show here at the beginning, the material is more fluid, okay, because G double prime is higher than G prime. Okay, with time there's a crossover and then it plateaued. Okay, generally what they call about this, about the gel crossing over. Okay, and then when you know what the gel is formed, when it starts to plateau, I mean the strong material or gel has been formed. Okay, I will just leave this one. You can measure the gel point by having different frequency. We're not going to detail. Okay, one other example where you can look at using rheology is to measure or estimate the glass transition temperature of food material. If you think about it, what is glass transition is, in terms, this is more or less about molecular mobility. Okay, if you look at molecular mobility, there are three types people generally talk about: vibration, rotation, and translation. I don't know whether you know about it. Vibration, you just vibrate. You can't do anything. You just move sideways. Rotate, you can rotate. A molecule can rotate. Okay, like water. If you put it in a microwave, it can rotate. Okay, and translate, it can move from one side to the other. And they say that the gas transition is the change from what's called vibration, okay, to translations stage. Okay, and then when the material move from when it goes through the glass transition temperature, okay, what tend to happen? It tend to what's called soften. Okay, so their moduli, especially your storage modulus, tend to change and become lower. So with rheology, you can measure that, okay, within the linear viscoelastic range. So if you have a module, if you measure the modulus, you will see some, you will get a material like that. It will be high modulus at the beginning, okay. As you increase the temperature, it softens because there is some what's called change in terms of the glass transition. There is already from vibration, okay, to translation stage, to rotation and translation, and then your material become more amorphous, okay, and then the moduli decrease, and then you can look at that, you can compare different material using rheology if you do a temperature sweep. Okay, the same thing, if you do a temperature sweep, you can get a peak here, or tan delta can have a peak, and then you can look at the tan delta peaks. Generally, people can also use it as a glass transition temperature. What is the importance of glass transition? Is in terms of shelf life and molecular mobility. So if you store something which is below the glass transition, it's very stable and have a long shelf life compared to above, if you store something above the glass transition temperature. Okay. So another way where you can look at the measurement is really looking at the what's called the viscous component, which is the N star, okay, or the what's called the eta star when you get it in terms of rheology, when you do a small deformation. And there has been, in terms of sensory thickness and in terms of the eta star here, which is what's called complex viscosity. Okay, with increase in the complex viscosity when you do a rheological measurement, the sensory thickness also increase. Another example here, you can also look at the beta lactoglobulin when it's gelling, like we said here. Okay, and beta lactoglobulin is a heat-induced gelation because it's a milk protein. So when you heat it, okay, it becomes thick until it becomes more or less, it thicken, okay, and then it can gel. So what tend to happen here, if you look at the phase angle here, when it's close to, very close to 90, because it's very fluid, When it comes to 0, it's more like a solid material, and it's more like a solid material. So this decreases the tan delta, but your storage modulus, it becomes stronger. The highest storage modulus means you have a stronger network. So you can see that it's forming a network here until it stabilizes. You can look at gelation properties, which is a heat induced if you do, like, for example, a temperature sweep, which you increase the temperature also. Okay, we talk about gelling, increase in G prime. I already told you about this one. Another example to see what sort of relative humidity you can store your biscuit or your cookies. So if you look at the storage modulus here, as you increase the relative humidity, your storage modulus decrease, okay? And your phase angle tend to increase. So you can see here from maybe about 20, 30, and it starts really looking bad when it's about 60. So maybe you should not store your sample higher than 60% relative humidity. That's an example. Okay, so try to give it less than 60% relative humidity. And Indonesia there, what sort of relative humidity generally you get? If I may ask, 75, 80%?
Yeah. Yeah, more than 70%, I think.
Yeah, like in my place, especially now in winter in Pretoria, it will be 40 or less. Okay, but if I go down in Durban, which is the coastal area, during summer also it's about 75, 80% relative humidity. So just to show you what is the maximum relative humidity, one can think about storing sample without it absorbing the moisture and changing the rheological properties and changing the snap properties of cookies. I already told you about the glass transition. So you can see here, this is the E prime, or they call about G prime is most in terms of shear. And if you look at in terms of tension for bioplastic films, you will do it in tension. So the E prime will just decrease here. And you can check that this can be regarded as the glass transition temperature in the middle here. And the tan delta also peak. That can be regarded as the glass transition temperature. Okay. All right. So where can we use in food science and technology? Really measuring viscoelastic properties of food and correlating with sensory, then use it as a quality control, as sensory is time consuming, expensive, and can also have a lot of ethical. So for example, to do sensory evaluation, you need to apply for ethics, whereas here you don't need. I mean, yeah, you need to be ethical what you do, but you don't need to apply for ethics because you're not using human being. Understanding a lot of scientific phenomena like gelling, glass transition, doing some fundamental studies. I don't know if some people want to tell me more about where else can you use rheology in your reading and what you learn at in your lectures, please. Anyone?
I think they are a little bit shy, Professor.
No, no, that's fine. Maybe anyone? Have you done dough rheology in any of your lectures?
Yes, we did some experiments, and then the students who are working with their thesis right now, also some of them do the rheological measurement.
Oh, okay, no, that's fine. No problem. Okay. See, I just want to give you an example here. These are just two types of salad dressing that have some herbs inside. Okay, and this is at the beginning here, and then this is after 15 minutes. Okay, so if you are looking something, this is your right hand side and this is your left hand side. Okay, can I basically just hold on here? pen. Okay, so if this is A and this is B, as a consumer, if you want to buy a salad dressing, which one will you buy, A or B? Maybe you can put it in the chart. Let's see. Okay, so this is also A, B. Which one is more appealing for you? After you just buy it, after sometimes all your herbs sediment there compared to here, compared to B. So which one will you prefer to buy?
One
I
answer
prefer
said
B.
A. Oh, yeah. And then B.
Yeah, I prefer B.
Yeah, B, yeah. Okay. Obviously, I mean, because if you pour it, I mean, you will get A, if you pour it, you won't get any herbs. Am I right? Herbs will be only down, or it will be settled down. Okay. Whereas here it's all over, it's quite homogeneous. Am I right? So generally, this is what the good quality one will be. Okay, you don't want sedimentation to happen, but how do you do that? You need to make sure there is the density is so you get a density that you get a viscosity, sorry, a thickness here, viscosity that doesn't allow the material to sediment at all. Okay, so when you talk about viscosity, this is the last part when you talk about rheology. We won't go into a lot of detail of viscosity measurement. I'm sure you've used it, you've done it. We talk about two type of viscous behavior, Newtonian and non-Newtonian. So Newtonian is shear rate is directly proportional. Okay, shear rate is directly proportional to shear stress. Okay, viscosity is given by the slope of shear stress and shear strain. So if you do a graph, okay, if this is the shear strain, which is the gamma dot, okay, and this is the shear stress here, which is sigma or tau, you can put tau here, okay, you will get more or less like a straight line for Newtonian, okay, and then the slope here will be the viscosity measurement. So you can see the slope is the same all over whether you change the shear rate or not. Okay, so the viscosity is given. So example, and this is so shear rate, so Newtonian fluid or this is not affected by the shear rate. So example of water, sugar syrup, most honeys, edible oil, filtered juice, and milk, for example. So this constant viscosity here of all shear rate. So see, for example, if you think about water here and a sugar solution at 10% and a sugar solution at 25%. So the 25% here sugar solution, okay. This is 10% sugar solution. And this is just water, which is 0%. Okay. All right. So what I'm trying to show here is you will need more force to turn the viscous one. And this is what it's trying to show you here. Okay. Your shear stress and shear strain here. Shear stress here and shear strain. Okay. So if you look at the slope here, it's the same all the time. It's not affected by the shear strain. So this is how it is, sorry. So this is your mobile, intermediate, and very viscous. So this is your 0%, this is your 10% sugar solution, and this is your 25%. Okay. So this is what is Newtonian fluid. But there are most material are non-Newtonian. And it can be divided into several types. It can be plastic or Bingham. I mean, how the yield stress means you have a minimum force that you need to apply for it to really start moving. For example, tomato ketchup. mayonnaise or whipped cream. That's why if you put it in a bottle, it doesn't come out. You need to press the bottle for it to come out. You need to, yeah, shake. And it doesn't come out that easily. You need to have certain amount of force. Pseudoplastic or shear thinning, shear stress decrease with shear rate. Example, salad dressing that contain biopolymers like xanthan gum or gelatinized starch suspension. So viscosity decrease with shear rate. Okay, this happened to most biopolymers in solution. Dilatant flow is shear stress increase with increase in shear rate. For example, this is only raw starch suspension. If you start stirring raw starch, it form like more like a dough. Okay, then it become it become more. You need more energy or more force to move it. Same thing when you are cooking starch, the same thing happen. It become dilated, it become increase in viscosity, not already gelatinized. If it's already gelatinized, it will be shear thinning. But when you're making it to gelatinize, when you're gelatinizing your starch to form a starch base, I would say it's more like a dilating flow. Okay, here viscosity increase with increase in shear rate. Here viscosity decrease with increase in shear rate. This is what tend to happen here. So like if you look at viscosity here, okay, and the thing is Pascal dot S, Pascal second here, and this is shear rate here, which is gamma dot, and gamma dot, the what's called the unit is reciprocal second. Sorry. Okay, shear thinning will be like that. Okay, shear thickening will be like that. Okay, and remember Newtonian will be just a straight line. Sorry. Okay, and yeah, so remember shear stress divided by shear rate is the viscosity. But you have, first you need to look at shear stress divided, shear stress and a shear rate graph. And this is how it look like. Okay, this is shear thinning. Okay, and if you think about here, the slope is the viscosity. Can you see here? So the viscosity here is high, the viscosity here is low. For pseudoplastic, okay, the shear thinning, okay, and dilatant, if you look at the viscosity here, you will see with increase in shear rate, the slope increase, so the viscosity increase here. Okay, Newtonian, like I explained to you, is the same all the time. Okay, all right, the same thing here, whether it's pseudoplastic or plastic type fluid, the viscosity decrease with shear rate. Okay, so why is it important? See, for example, here. Yeah, so this is a syrup, like maybe 20% or 30%. The viscosity is still the same with the shear rate, and the viscosity, the viscosity stays the same at different shear rate. But if you look at xanthan, it's shear thinning. So why is it important in food industry? Because different process has different shear rate. Sedimentation very low. Tank maybe about 10 to 1. Chewing about 100 to from 10 to 100 shear rate. Spreading is very high shear rate. Okay, for example, if you look at your bread, your margarine, it's quite it's not a fluid, but the moment you can spread it nicely for spreading. Okay, for pipe flow. Okay, for tank. All right. So chewing, for example, there is a shear rate start maybe 10 to almost 100. Okay, 10 is mostly for infant, which is 6 months, and 100 can be nice adult. Okay, or 10-year-old. Okay, so depending on what sort of energy. So for example, here you can see already there is a huge difference of viscosity between 10 and 100. Okay, so a child, for example, which is 6 to 12 months, there's a problem, like explained to you. Maybe in Indonesia, here, most people use porridge, okay, sometimes as their food. For example, they eat maize porridge, which is very thick, as a staple here. So people who are doesn't have a lot of money, if they go to the shop, they will only buy maize meal and some sugar, some tea, and some oil and some vegetables. And when they go home, and baby food is quite expensive. So when they go home, they tend to make their porridge. But the babies that are from 6, the infant from 6 to 12 months, they can't process because it's too viscous. So what people tend to do, they tend to dilute it to make it similar to the viscosity of milk. Okay, so the viscosity of milk, then when they dilute it, they dilute the energy and they dilute the protein. So the infant doesn't get enough energy and doesn't get enough protein from 6 to 12 months, especially if they are not also breastfed at the same time. So these children tend to have what we know as protein energy malnutrition, or they can also actually try to what's called this protein energy malnutrition. So they tend to what's called cause stunting. For example, in South Africa, almost 29 to 30% of children are still stunted. Okay, and one reason is that what type of food they have at home. So this is where one can apply our principle of rheology to find out how to can make baby food with lowering the viscosity. Like in my research group, we've done some work how we can make these cereal, like whether it's maize, whether it's wheat, or whether it's sorghum, how can we make it lower viscosity without changing the properties of the flour? And one example is we can heat process it in microwave, okay? Not to cook it, to change the molecular configuration, and this affect the what's called the microstructure during cooking. And when the microstructure is affected during cooking, the viscosity is decreased. When you cook it, it becomes more flowable, reduction in viscosity. That's an example. So the idea here is between Newtonian and non-Newtonian also is we never do a single measurement. Because if you look at syrup here, it's 10 to the power 1, which is 10 Pascal second. At shear rate more or less, what's called 10 to the power of 0 is 1. At shear rate 1, it's 10 Pascal second as well as xanthan. But if you look at lower shear rate, xanthan is far higher than syrup. And if you look at higher shear rate, xanthan is far lower than, yeah, okay. And we talk about, remember, we talk about infant here, I will say more or less they got very low shear rate because of their mastication properties, how their mouth is, what's called the mouth, the tongue, and the palate in the mouth are. Okay, so this is what I wanted to show you a little bit, and I put some YouTube videos there what people can read, and I hope that YouTube is still there, okay, that I used to put. I don't know, so this is for me what I wanted to show for the, yeah, what I wanted to show in terms of the viscosity, yeah, and rheology lecture today. I don't know if anybody has any question or comment.
Okay. We will now proceed to the discussion session. I would like to invite participants to ask up to 3 questions. Please raise your hand and I'll give you the opportunity to speak. Please, anyone?
Okay, let me just also try to open the video.
Okay, so Professor, as you said that in order to easier to understand any topic, yeah, not only rheology topics. We need to familiarize ourselves with the terminology, right? So I think
Yes.
this one is quite challenging because sometimes we just want to jump into the theory, into the material without knowing the terminology first so that we can get confused in learning the topic. Yeah.
Yes. So no, I think hopefully, I mean, today some of the terminology we explain it, okay, and it can
Yeah.
help them, yeah,
Yes, you
to
really help
understand.
to elaborate the terminology to
Yes.
understand the definition of each terminology. So
Yeah. Mhm.
it's very helpful to
So,
understand.
yeah, so I will say that for me, I mean, rheology where I use it a lot is like for baby food. That was very interesting to understand that. And we also use rheology, microstructure, and molecular structure. We bring it together. Okay. And also look at the chemistry. For example, when we're talking about the baby food, I mean, a simple microwave, what tend to happen? They denature the protein. And when you denature protein, it becomes hydrophobic. And it becomes hydrophobic, and then it coat the starch. Okay. So when it coat the starch, then when you cook it, your starch is not available to form a paste of high viscous paste. So we did rheology to measure it, as well as we did microstructure to look at what is happening to the starch granule. Okay, and also we do some chemical analysis, like to show that the protein has denatured. Okay,
So
so this is an
this
example. Yeah.
so this
Sorry, Dr.
rheology,
Tina?
yeah, so this rheology help us to develop foods for certain needs. Yeah, for example, for elderly groups,
Yes.
for
Good.
baby
Children.
group.
Yeah.
That's very important because they have probably different structure of uh
The
what is it?
mouth.
Yeah, their mouth.
Yes. Okay. And rheology also can help you to understand certain scientific phenomena. I think if, especially if you're doing a PhD level, you can use rheology as a tool. And what I will say is rheology is a science in itself. Some people tend to say, oh, I'm just going to measure viscosity, or I'm just going to measure the viscoelastic properties of food. I don't think it's just that straight, simple, like measuring a protein content of food. Rheology in itself is a science. Okay, I will tell you, I'm still learning. I can't do, being a food scientist, I can't do fundamental rheology work. So understanding these small principles help you to apply it. But for me, I mean, to do these fundamental work where there is a lot of formulas and maths and physics, I get lost. It's not my expertise.
I have a student that is doing her thesis about the mayonnaise that she want to
Yes.
develop a low fat mayonnaise, yeah, by substitute the uh, some of
Oil.
the yeah, the oil with the what is it, the uh, fiber, yeah, but
Yes.
the rheology, the consistency is quite different when we reduce a lot of oil, so it's quite
Yes.
challenging.
Challenging. Yeah. I think these very important. I think, for example, again, for there has been a lot of fundamental work done on measurement the viscosity of mayonnaise because it have a lot of oil there. As far as I know. Okay, so you need to use, like, for example, serrated probes because there's a slip that happened. If you use a system, it might not work for mayonnaise because there's slip phenomena and you don't measure the shear rate properly. I mean, the shear stress properly. Yeah. Okay, there is somebody here. Okay. Yeah, that's it.
Uh,
Got it. Somebody on the chat. Yeah.
Okay, anyone, if you want to post your questions in the chat, please.
Okay. Okay.
Anyone?
Okay, is somebody?
Okay.
Yes,
Yeah,
Faith.
Faith. Please, Faith.
Hello, my name is Faith.
Hello.
May I ask a question about the rheology? Because when I saw the example you have given with the oil and the herbs one, the A and B, where one of them has more sediment than the other, I would like to ask, how do you create uh, uh, like the specific type of rheology for specific target markets? Because I sometimes see that there are products more like A, where there's more sediment, because people think that like, oh, it looks more natural, because usually food does create sediment, and consider B as like, oh, they have additives or something. But there are also people who thinks that B is better because, oh, it looks prettier, and it looks more promising. So is that made for specific target markets, or is there other specific methods that you use to create a specific rheology for a product?
Yes. Faith, I think you already answered your question also by talking, which is very good thinking. I will say you said for specific market. That's very important. And you use the word better and improved. Okay. In science, when you do scientific research and you publish papers, I always trying to question when people try to say, oh, this is better. A is better than B. But it's also, I mean, maybe A is for a specific market and B is for a different market. You get where I'm coming from. So that's why I want you to, when you have to have, if it's better or it is improved, you always need to have the reference and what the consumers want. You're absolutely right in saying that sometimes a slight sedimentation is fine, okay, compared to, yeah, in most markets, for example, here, I mean, sedimentation is not really what people is looking for. Like if you have, that's why, for example, if you have juice, you clarify it. Okay, but if you have a cloudy apple juice, you need to make sure that it's not, it doesn't really sediment. Otherwise, if you first serve the top part, then somebody will got more a thin viscous material. And if you what's called serve the last portion on the bottom, it will be thick. So it's not consistent in terms of the viscosity. So, and quality is really about consistency. Are you with me, Faith? But at the same time, you're right, it depends which market you want to go for. Yeah. And
Thank
as
you.
scientists, I always discourage my students to use the word, discourage them so that they don't use the word better and they don't use the word improve. Always say increase or decrease, unless if you have a specific product that you are changing to make it better based on the sensory or based on the quality parameters that you set from the beginning.
Okay, thank you, Faith, for your questions, and Professor Emalux for your answer. Anyone else want to ask Professor? Oh yeah, we have
Correvano.
Revano. Please, Revano.
Okay, good afternoon, Professor. I would like to ask, when we're developing an instant product based on sorghum, what aspect of rheology should we put more focus on when developing it, and how does it, like maybe which part of it that actually matters for the product itself?
Okay, so Revano, I think it depends what market and what is your brief. Okay, if you're developing a baby food, for example, viscosity is very important. Okay, and from a rheological point of view, I think one should not look also when you develop a product, you know, not need to look at rheological, but you also need to look at the nutritional value of the food. So, for example, for us, for porridge, for example, you need to, for example, you can structure design in such a way that you can, for baby food, for example, you keep the nutritional value or the nutritional properties without, like, let me explain to you. Okay, one way of to reduce the viscosity where most baby food are made, especially in South Africa, is through extrusion. You know, extrusion, you depolymerize your starch and then the viscosity decrease. Okay. But if you use the same porridge now, if you use it for an adult, it's not good because it has a very high glycemic index because it's already depolymerized. So the food is digested very fast and increase the uh, blood glucose level. The same thing maybe for 6 to 12 months, this is fine. But as we grow, if the same porridge is being used for 2, 3 years, then it's not good because we want also to reduce slightly the what's called the glycemic index. So depend on your market if you want to do a porridge. Okay, so I think this is one example that I can give for sorghum. I think sorghum, more importantly, what we've done here, for example, we've done project like we make expanded snack, okay, with added fiber where the sensory properties is similar to refined without the fiber, but obviously it has a lower glycemic index. So the viscosity here plays an important role because you increase the soluble dietary fiber. Okay. For baby food, I will say that you need to reduce the viscosity. Okay, and for adult, maybe you need to increase the viscosity so that there is this effect, the nutritional effect in terms of the increased dietary fiber. I can make it more nutritious. And nutritious means not quick energy, it's like slow energy release. Does it make sense what I'm saying? Yeah.
Yes, sir. Thank you for your insight.
Yeah.
We have another participant who want to ask. Yes, please,
Yes,
Clarissa.
Clarissa. Yeah.
Hello, sir. Good afternoon. My name is Clarissa. I'm from Food Technology, and I would like to ask you two questions. The first is about a debatable question. Does true yield stress actually exist, or is it just a measurement limitation? Some rheologists argue that every
Can,
material will flow if you wait long enough or apply even the tiniest force. Others also mention that for materials like ketchup, the internal network of tomato solids creates a genuine physical barrier that prevents any movement below a specific threshold. Like, does it true that stress actually exists, or is it just a measurement limitation? That is my first question. And then my second question
yeah. Can,
is the tuning of
sorry,
ketchup.
sorry, Clarissa, let's go, Clarissa, let's go one by one. Sorry to bother, but I couldn't understand, hear you properly. I don't know whether Tina, did you hear properly? Because I couldn't hear properly.
Yes, the audio a
Can
bit
you
not
repeat,
clear.
please? Yes, I'm very sorry. Can you repeat, please, if you don't mind, your first question?
Okay, I will repeat my first question. Okay. Does true yield stress actually exist, or is it just a measurement limitation? Okay. Because some rheologists argue that every material will flow if you wait long enough or apply even the tiniest force. Others also say that for materials like ketchup, the internal network of tomato solid creates a genuine physical barrier that prevents any movement below a specific threshold.
Yes. So yeah, I understand. Like for ketchup, there is time dependent, okay, and time independent. Yes, I think this is what some material are like that. With certain time, it will start flowing. Some will not flow. I mean, it's similar to what they talk about the yield stress. So you need to have the minimum force to start moving the material. But again, here I will say you, some people doesn't believe in yield stress. I think some rheologists doesn't believe also in yield stress. Okay, so it's more like these are more fundamental type research that people do, and I don't do that. So, but I can tell you what I know here. Okay, hopefully that answers your question. So the different ways. I think there are also different theories or hypotheses people look at when they do rheology. Like I told you, some people say that there's no such thing as yield stress. Yeah. Okay. All right. Does that make sense what I'm saying now? It's Clarissa, I think. Yeah.
Mm, okay.
Yes.
And also,
And your second question?
now my second question is, I'm more like about ketchup is described simply as shear thinning. However, if you stir ketchup at a constant speed, it continues to get thinner over time, or like it's thixotropy. Is it right? Is it called thixotropy?
Yes,
Yeah.
yes, yes.
Um.
Yeah. So
Okay.
it, yeah, I agree with you. It depends on what is the ketchup made up of. I think if it's a pure tomato purees, it can be thixotropic, I think, yeah. And then if you look at what is it called? Yeah. If it's pure tomato, then it can be, yeah. Uh, but if you add, it depends on the ingredient. The moment you add other biopolymers there, like starch, then it becomes shear thinning. It depends on the microstructure, how the polymers are dispersed there. Does that answer your question? It depends on your ingredient, yeah.
So the
But they did
thinning
say the
of
pure
the
ketchup, yeah,
so the thinning of the ketchup.
ingredient can determine whether something can be from shear thinning to sometimes even have what's called. I think it's more like a Bingham fluid. I think I don't know whether if I understand, if I remember very well. Yeah.
So the result is of the rate of shear or the duration of shear.
Oh, I think ketchup. Isotropic. I just want to say that it depends on the ingredient. Yeah. What you are having. But if the moment you put a biopolymer there, like gelatinized starch, it will become shear thinning. Yeah.
Thank you very much. That's all for my question.
Yeah.
Okay, I think we have come to almost the end of our lecture today, Professor. So
Yes. Thank you.
um, I think we now reach the moment to express our sincere appreciation to our distinguished speaker. Yeah. On behalf of the Technology Business University, we would like to present an e-certificate of appreciation to Professor Naushad Imambooks for the valuable knowledge and the insight shared in today's session entitled Introduction to Food Rheology and its Application in the Food Industry. So as a token of our gratitude, uh, Amelia, please share the e-certificate, please. Oh, the e-certificate, please accept this e-certificate, Professor Books, and
Yes.
we extend our deepest appreciation to you from the University of Pretoria for sharing valuable insights and perspectives that contribute to the advancement of food science and sustainable food processing and food development. We hope today's session has inspired new ideas for the students who probably next semester or next year want to do their thesis project, and then to strengthen our academic industry connections, encourage more exploration in the field of food rheology. So we look forward to welcoming
Yes.
you again at our future events. So thank you once again, and please give a round of applause for Professor Nausat Imam.
All right, thank you very much. It was a great pleasure also for me to share a little bit of what I know in food rheology.
Can we
Okay.
have a photo
All right.
session, Professor?
Yes, yes, please. It's not a problem. Yeah, I don't know how you would do it, but yes, yeah.
Okay, I think I asked Pak Andres, could you please help us to capture?
Sure.
And everyone, please open your camera and prepare your nicest smile.
Okay, there are 7 pages here. So please open up your camera. I will take the picture, yeah. Okay, 1, 2, and 3. Okay, page 2. 1, 2, and 3. Page 3. Okay, page 4. Page 5. Page 6. And page 7. Okay, that's it. Thank you so much.
Okay, thank you. I see that somebody was asking for my contact detail, but please, you can ask Dr. Tina. She has all my contact detail. Yeah.
Okay, I will share your contact details. Once again, thank you very much, Professor Nausat Imam Books, and have a wonderful day, everyone.
Okay, you too. Keep well then. Thank you. Bye-bye.
Thank you very much. Bye-bye.
Thank you, sir. Have a nice day.
Bye.